In this video, we are looking at section 1.1, which is the first part of our pre-calculus review. This section and most of this chapter focuses on material you've likely already seen many times in the past. I'm going to make this an abbreviated overview. If you have questions on these topics, double check your textbook, then email me or come to office hours. So first, we're going to talk about the real number line. We can represent real numbers geometrically by points on a real number or coordinate line. Arbitrarily select a point on a horizontal line to represent the number 0. This point is called the origin. A point at a convenient distance to the right of the origin is chosen to represent the number 1. This determines the scale for the number line. Each positive number lies an appropriate distance to the right of the origin, and each negative number lies at an appropriate distance to the left of the origin on the number line. A one-to-one correspondence is set up between the set of all real numbers and the set of points on the number line. Only one point on the line is associated with each real number. Conversely, exactly one real number is associated with each point on the line. The real number that is associated with a point on the number line is called the coordinate of that point. In this class, we will often restrict our attention to subsets of the real numbers. If X represents the number of cars rolling off an assembly line each day, then X must be non-negative. That is, X is greater than or equal to 0. If the plant management decides that daily production must not exceed 200 cars, X must satisfy the inequality 0 is less than or equal to X is less than or equal to 200. We are mostly interested in 3 types of interval: open intervals, closed intervals, and half-open intervals. An open interval includes only the set of numbers that lie strictly between its endpoints. If the endpoints are A and B, where A and B are real numbers and A is less than B, then the open interval is the set of all real numbers that satisfy the inequality A is less than X is less than B. This set can be written as A comma B in parentheses. A closed interval includes only the set of numbers that lie between its endpoints and the endpoints themselves. If the endpoints are A and B with A less than B, then the closed interval is the set of all real numbers that satisfy the inequality A is less than or equal to X is less than or equal to B. This set can be written as A comma B in brackets instead of in parentheses. A half-open interval includes one of its endpoints, but not the other. If the endpoints are A and B, A less than B, 2 half-open intervals are possible. A is less than or equal to X is less than B, and A is less than X is less than or equal to B. These sets can be written as A comma B with a bracket on the left and a parenthesis on the right, and A comma B with a parenthesis on the left and a bracket on the right, respectively. All of these intervals are finite intervals, since A and B are real numbers. We also encounter infinite intervals. Infinite intervals may be the whole number line from negative infinity to positive infinity, or half lines from A to positive infinity, not including A, from A to positive infinity, including A, from negative infinity to A, not including A, and from negative infinity to A, including A. Because infinity is not a real number, the infinite side of the interval is always open. Briefly, B to the n is B times B times B times a whole bunch of other B's times B, where there are n factors of B. Here, B is called the base and n is called the exponent. If n equals 0, then B to the n equals 1. If n is a positive integer, then B to the 1 over n equals the nth root of B. If this number exists, it is called the nth root of B, which I just said. If n is positive, B to the negative n is 1 over B to the n, and 1 over B to the negative n is B to the n. We have some laws of exponents. A to the m times A to the n equals A to the m plus n. A to the m divided by A to the n is A to the m minus n, where a is not equal to 0, because if a is equal to 0, we're dividing by 0, and we can't do that. A to the m raised to the nth power is a to the m times n. AB raised to the nth power is a to the nth power times b to the nth power. And a over b to the nth power is a to the nth power divided by b to the nth power. An algebraic expression of the form a x to the m, y to the n, where a is a real number and m and n are non-negative integers, is called a monomial. The degree of the monomial is the sum of the powers of its variables. For example, the monomial 7x squared times y to the fourth has power 6, or has degree 6. A polynomial is a sum of 2 or more monomials. The degree of a polynomial is the highest degree of its component monomials. The degree of 3x squared plus 7y cubed minus 2xy is 3. Terms that have the same variable part are called like or similar terms. Constant terms are always similar. Like terms may be combined by adding or subtracting their coefficients. To add or subtract 2 or more algebraic expressions, remove the parentheses or parentheses around them, then combine like terms. The resulting expression is written in order of descending degree. Order of monomials with the same degree do not matter. For example, 2x to the fourth plus 3x cubed plus 4x plus 6 minus 3x to the fourth plus 9x cubed plus 3x squared is equal to 2x to the fourth plus 3x cubed plus 4x plus 6 minus 3x to the fourth, because that negative gets distributed through the whole system there, minus 9x cubed minus 3x squared, which is equal to 2x to the fourth minus 3x to the fourth plus 3x cubed minus 9x cubed minus 3x squared plus 4x plus 6, which is negative x to the fourth minus 6x cubed minus 3x squared plus 4x plus 6. When algebraic expressions are multiplied, each term of one algebraic expression is multiplied by each term of the other. The resulting algebraic expression is then simplified. For example, x squared plus 1 times 3x squared plus 10x plus 3 is equal to x squared times 3x squared plus 10x plus 3 plus 1 times 3x squared plus 10x plus 3, which is 3x to the fourth plus 10x cubed plus 3x squared plus 3x squared plus 10x plus 3, which is 3x to the fourth plus 10x cubed plus 6x squared plus 10x plus 3. Some useful product formulas. A plus b squared is a squared plus 2ab plus b squared. A minus b squared is a squared minus 2ab plus b squared. And a plus b times a minus b is a squared plus b squared, a squared minus b squared. Factoring is the process of expressing an algebraic expression as a product of other algebraic expressions. By applying the distributive property, we may write 3x squared minus x equals x times 3x minus 1. To factor an algebraic expression, first check to see whether any of its terms have common factors. If they do, then factor out the greatest common factor. In the example above, 3x squared and x have the common factor x. Sometimes an algebraic expression may be factored by regrouping and rearranging its terms so that a common term can be factored out. For example, 2ax plus 2ay plus bx plus by equals 2a times x plus y plus b times x plus y. So that's 2a plus b times x plus y. Product formulas used in factoring include the difference of two squares, x squared minus y squared equals x plus y times x minus y. The perfect square trinomial, x squared plus 2xy plus y squared equals x plus y squared. The sum of two cubes, x cubed plus y cubed equals x plus y times x squared minus xy plus y squared. And the difference of two cubes, x cubed minus y cubed equals x minus y times x squared plus xy plus y squared. The factors of the second degree polynomial with integral coefficients x squared plus qx plus r are ax plus b times cx plus d, where ac equals p, ad equals q, and bd equals r. We can use a trial and error method to factor polynomials of this form. To factor x squared minus 2x minus 3, first observe that the only possible first degree terms are x, and the product of the constant terms is -3. So we have these possible factors: x minus 1 times x plus 3, or x plus 1 times x minus 3. We multiply each of these to find that x plus 1 times x minus 3 equals x squared minus 2x minus 3. Roots of polynomial equations. Given a polynomial equation of degree n in the variable x is an equation of the form a sub n to the times x to the n plus a sub n minus 1 to the times x to the n minus 1 plus a bunch of other stuff plus a sub 0 equals 0, where n is a non-negative integer and a sub 0, a sub 1, at c dots is supposed to be a series of dots. Sorry, I forgot to hit a slash or something. And a sub n are real numbers with a sub n not equal to 0. The roots of a polynomial equation are the values of x that satisfy the given equation. One way to find the roots is to factor the polynomial and solve the resulting equation. For example, the polynomial equation x cubed minus 3x squared plus 2x equals 0 may be written as x times x minus 1 times x minus 2 equals 0. Thus, the solutions of the equation are x equals 0, x equals 1, and x equals 2, because any of those will make the whole equation equal to 0. To find solutions to a second degree or quadratic equation expressed ax squared plus bx plus c equals 0, we can use the quadratic formula x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. This is sometimes remembered by singing it to the tune of Pop Goes the Weasel. X is equal to negative b plus or minus square root of b squared minus 4ac all over 2a. When I taught high school, I did this repeatedly until my students were hearing it in their sleep. I'm not going to do that to you. For example, to solve 2x squared plus 5x minus 12 equals 0, we see that a equals 2, b equals 5, and c equals negative 12. So we plug those values into the respective variables and set up this equation. X equals negative 5 plus or minus the square root of 5 squared minus 4 times 2 times negative 12 all over 2 times 2, which is negative 5 plus or minus the square root of 25 plus 96 over 4, which is negative 5 plus or minus the square root of 1 over 4, which is equal to negative 5 plus or minus 11 over 4. Then x equals negative 5 minus 11 over 4, which is equal to negative 16 over 4, which equals negative 4. Or x equals negative 5 plus 11 over 4, which equals 6 over 4, which is 3/2.